One of the key aspects of this process is the use of flame cutting, combined with a rotating ring mechanism. The torch is moved in and out of the ring, with the speed of rotation precisely controlled by a precision gearbox. This setup ensures that the cutting process remains smooth and efficient, eliminating friction commonly found in conventional cold steel cutting systems. The result is clean, accurate cuts with evenly spaced teeth, matching the exact design specifications. An integral part of the process is the use of profile cams and speed cams, which control the tooth form of the gear or sprocket. These cams ensure that the teeth are consistent and match the design requirements. Cogmatic, the manufacturer, maintains an extensive library of pre-designed cams, but can also create custom cams to fit specific tooth forms, offering flexibility for unique design needs. The materials used in manufacturing range from low to medium carbon steel plates to rolled seamless forgings and bar stock, all of which are carefully selected for both cost-effectiveness and performance. Additionally, the process is adaptable for development work with minimal tooling requirements, making it ideal for prototyping or custom orders. Beyond the initial cutting, the process also includes blanking, flame machining, chamfering, and tooth cutting, as well as induction heat treatment, welding, and packing, all performed in-house. This comprehensive approach ensures that large gears and sprockets are produced with high accuracy and quality, meeting the exact needs of customers for a wide variety of industrial applications. Forged blanks are precision formed under high pressure, enhancing strength, grain alignment, and durability before machining and gear cutting processes. Turning shapes the forged blank using a rotating cutting tool. Gear cutting uses advanced CNC machines to precisely form spiral bevel teeth, ensuring optimal meshing accuracy, strength, and gear performance. Nitriding hardens gear surfaces, enhancing wear resistance and durability. Spiral bevel gear grinding refines tooth surfaces to micron-level accuracy, ensuring smooth meshing, reduced noise, and extended lifespan. Precision grinding corrects distortions and improves overall gear transmission performance. Electron beam welding uses a focused electron stream in a vacuum to fuse the bevel gear and shaft with extreme precision, ensuring deep, high-strength welds with minimal thermal distortion. Ultrasonic testing uses high-frequency sound waves to detect internal flaws or discontinuities in welded and machined components. Reflected signals from imperfections are analyzed, ensuring structural integrity without damaging the part, making it ideal for critical aerospace applications. Radiographic testing, RT, involves using X-rays or gamma rays to inspect the internal structure of welded joints and components. The radiation passes through the material and exposes a photographic film or digital sensor, revealing internal defects like cracks, voids, or inclusions. RT ensures the weld quality meets strict aerospace safety standards. A post-nitriding cooling or rinsing process, using water to stabilize treated parts, remove residual chemicals, and prevent oxidation, ensuring surface integrity and consistent hardness. Magnetic particle inspection detects surface and near-surface cracks in ferromagnetic materials using magnetic fields and fine iron particles. Superfinishing smooths surfaces to ultrafine finishes, reducing friction, wear, and improving the lifespan of mechanical components like gears. Runout inspection checks rotational accuracy and alignment of rotating components. Surface roughness inspection measures texture irregularities on a part's surface, ensuring smoothness for optimal performance, durability, and proper functioning. A 3D measuring machine uses advanced sensors, typically laser or optical, to capture precise measurements of a part's dimensions in three-dimensional space. It creates detailed digital representations, checking for deviations from specified tolerances. Gearbox assembly involves fitting together gears, shafts, bearings, and other components to create a functioning unit. Precise alignment, lubrication, and testing ensure reliable performance under operational conditions in aircraft or machinery. Rig testing simulates real-world operational conditions to evaluate the performance, durability, and reliability of mechanical systems like gearboxes. It helps identify potential issues under controlled stress before the component is used in flight. Main rotor hub assembly involves connecting critical components like the main rotor blades, pitch control mechanism, and gearbox to form the central rotating system of the helicopter. Precision alignment, lubrication, and thorough inspections ensure stability, control, and smooth operation, ensuring the hub performs reliably under dynamic flight conditions. The entry section prepares and feeds the coil into the mill, including uncoiling, leveling, edge milling, and initial alignment. Coil car lifts and positions steel coils onto the uncoiler. Uncoiler securely holds and unwinds the steel coil for processing. Hold down roll stabilizes coil during uncoiling to prevent misalignment. The coil peeler is a mechanical device used to initiate the uncoiling process by lifting and peeling the leading edge of the steel strip from the coil. It ensures a smooth and controlled start by separating the coil head without damaging the material. This helps feed the strip accurately into the pinch leveler, reducing downtime and manual intervention during line startup. The pinch leveler flattens and straightens the strip while feeding it forward, ensuring smooth entry into the processing line. The crop shear cuts the leading and trailing edges of the strip to remove irregular or damaged sections, ensuring clean strip ends for consistent welding and smooth downstream processing. Skewed conveyor aligns and transports strip laterally for edge milling. The edge miller is a critical component in the entry section, designed to mill and smooth the edges of the steel strip. This process removes any burrs, irregularities, or surface defects from the coil edges, ensuring precise edge geometry. Proper edge milling helps improve the welding process, enhancing the quality of the final welded seam and ensuring consistent pipe formation. The forming section shapes the strip into a round pipe form. The transition and breakdown stands gradually reshape the strip from flat to a circular profile. The breakdown stand further reduces the strip's thickness, preparing it for precise edge bending and forming. Edge bending stand shapes the strip edges to initiate pipe formation. The cage roll stand is a pivotal component in the forming section of the pipe mill. It uses a series of rolls to progressively bend the edges of the strip, guiding them toward a circular shape. This process forms the initial pipe structure, where the strip's edges are brought together, creating a cage configuration. The cage roll stand ensures accurate alignment and smooth edge bending, which is critical for the subsequent welding process to produce high-quality, consistent pipes. The fin pass stand is crucial for refining the pipe's shape and size during the final stages of the forming process. It applies controlled pressure to the edges of the strip, ensuring the two edges meet perfectly before welding. This stand fine-tunes the pipe's roundness, wall thickness, and overall geometry, ensuring uniformity. The fin pass stand prepares the strip for the welding section by achieving precise dimensions, which is vital for the quality and consistency of the welded seam. The high-frequency HF welder uses high-frequency electrical currents to heat and join the pipe edges. The squeeze roll stand applies pressure to ensure a strong, consistent weld seam during the process. The inside bead cutter removes excess material from the inner weld seam, ensuring smoothness and preventing defects in the final pipe. The outside bead cutter removes excess weld material from the exterior seam, ensuring a smooth surface and precise pipe dimensions. It helps improve the aesthetic and structural integrity of the welded pipe. The scrap winder collects and winds excess material, such as trimmed edges or scrap pieces, generated during the pipe manufacturing process. This system helps manage waste efficiently, promoting cleaner operations and recycling. The seam annealer applies controlled heat to the welded seam, relieving internal stresses and improving the mechanical properties of the weld. This process enhances the pipe's strength, toughness, and overall integrity. The pull-out stand ensures smooth and consistent movement of the pipe after welding, pulling it through the cooling section. It maintains tension and alignment, preventing deformation while controlling the pipe's speed. The air cooling stand cools the welded pipe using air circulation. The water cooling stand cools the welded pipe using controlled water jets, rapidly reducing temperature to ensure proper hardening and prevent distortion. The sizing stand shapes and controls the pipe's final diameter and wall thickness, ensuring uniformity and precision before cutting. The Turk's head adjusts the pipe's roundness and ensures uniformity by controlling its shape and alignment during the forming process. The inline marking machine applies markings or labels on the pipe's surface, indicating key information such as size, specifications, or batch numbers. The flying cutoff machine precisely cuts the pipe into desired lengths while it's still moving along the production line. It uses high-speed rotating blades or saws to ensure clean, accurate cuts. This machine is synchronized with the mill's speed, ensuring minimal disruption and maximum efficiency in the cutting process. The pull-out roll stand ensures smooth pipe movement, maintaining tension and alignment as the pipe exits the welding and cooling sections. The run-out conveyor transports finished pipes to the next stage, while the coil skid supports and stabilizes the coils during storage or handling. The flushing unit cleans the interior of the pipe using high-pressure water or air jets to remove debris, scale, and welding residues. This process ensures the pipe's internal surface is clean and free of contaminants before further testing or finishing. It enhances the quality and performance of the final product, especially for high-specification applications like API-grade pipes. The end-facing and chamfering machine is an essential part of the finishing line in a pipe mill. It performs two key operations: end-facing and chamfering. End-facing involves machining the ends of the pipe to ensure they are smooth, flat, and perpendicular to the pipe's axis. This is critical for ensuring proper fit-up during welding or joining operations in the field. Chamfering, on the other hand, involves beveling the inner and outer edges of the pipe ends to remove sharp edges and prepare the pipe for easier handling, welding, or threading. The machine can process pipes of varying diameters and wall thicknesses, automatically adjusting to specified parameters. It helps enhance the final appearance, functionality, and safety of the pipe. The precise machining also improves sealing performance in threaded or coupled pipe applications, making it indispensable for high-quality pipe production. The kick-in and receiver system is designed to guide and position finished pipes into the next stage of handling or inspection. The kick-in mechanism gently pushes the pipe from the conveyor onto a receiver or holding station, preventing damage or misalignment. The receiver then secures the pipe in place for operations like hydrotesting, inspection, or further finishing processes. The kick-out and roller conveyor system ejects finished pipes and smoothly transfers them to storage or the next processing stage. The hydrostatic tester is a critical component in the pipe mill's quality assurance process, used to verify the structural integrity and pressure holding capacity of each pipe. During testing, each pipe is filled with water and pressurized to a specified level, often exceeding the pipe's intended operating pressure, to simulate real-world conditions. This ensures that the pipe can safely withstand internal pressure, without leaking, deforming, or failing. The system typically includes sealing heads that close off both ends of the pipe, high-pressure pumps to introduce water, and sensors to monitor pressure levels and detect leaks or structural weaknesses. The test is performed according to international standards such as API 5L, API 5CT, or ASTM, depending on the pipe's intended use. Advanced hydrostatic testers are automated for efficiency and can handle a range of pipe sizes and wall thicknesses. After testing, the pipe is drained and moved to the next stage of processing. This step is essential for pipeline applications in oil, gas, and water industries, where safety and reliability are paramount. The offline ultrasonic tester is a non-destructive testing NDT system used to inspect the quality of weld seams and the overall wall thickness of the pipe after production. Using high-frequency ultrasonic waves, the tester scans the pipe to detect internal flaws such as cracks, inclusions, voids, or lack of fusion in the weld area. It can also measure uniformity in wall thickness along the pipe's length. This system operates off the main production line, allowing detailed inspection without slowing down the manufacturing process. Pipes are fed through the tester, where transducers and sensors evaluate structural integrity in real time. Any defects are flagged for further inspection or rejection. Ultrasonic testing ensures product reliability and compliance with strict industry standards like API, ASTM, or JIS. Manual UST involves technicians using handheld ultrasonic devices to inspect pipe welds and surfaces for defects not caught automatically. The varnish coating machine applies a protective layer to the pipe surface, preventing corrosion and enhancing appearance and durability. The end cropping machine trims the pipe ends to remove defects or uneven sections, ensuring clean, square edges that meet dimensional standards and improve fit-up for threading or coupling processes. The threading machine cuts precise threads on pipe ends, enabling secure connections for pipelines used in oil, gas, and water applications. The remelt process involves melting down aluminum scrap or ingots in a furnace to create molten aluminum. This step ensures the metal is purified and adjusted to the correct alloy composition for the desired product. Temperature and chemical composition are closely monitored to ensure consistency. The remelted aluminum is then poured into molds or directly transferred to the hot mill for further processing, ensuring optimal material properties for subsequent stages. The hot mill is a critical stage in the aluminum rolling process, where the remelted aluminum is transformed into larger, thinner sheets or coils. In this stage, the aluminum is heated to temperatures ranging from 400 to 500 degrees Celsius to make it more malleable and easier to roll. The metal enters a series of high-speed rollers, which gradually reduce its thickness by applying immense pressure. As the aluminum passes through these rollers, its microstructure is refined, improving its mechanical properties like strength and flexibility. The hot rolling process also improves the material's uniformity and removes any surface imperfections, preparing the aluminum for further reduction in the cold mill. The result is a thicker, more manageable aluminum product that can be further processed or coiled for transportation. Proper control of temperature, speed, and tension during hot rolling is essential to ensure the aluminum's quality and consistency. The cold mill further refines the aluminum after it has been hot rolled. In this stage, the aluminum is passed through rollers at room temperature, which reduces its thickness even further and enhances its surface finish. Cold rolling increases the material's strength, hardness, and precision. This process also improves the metal's dimensional accuracy and smoothness, making it ideal for applications requiring tight tolerances and a high-quality surface. The aluminum sheets or coils produced are thinner and more durable than those from the hot mill. The finishing stage involves several key processes that prepare the aluminum for final use. After cold rolling, the aluminum undergoes annealing, where it is heated to a specific temperature and then slowly cooled to soften the material, improving its workability. Cutting follows to ensure the aluminum is trimmed to the desired dimensions. Surface treatments, such as coating, polishing, or etching, may be applied to enhance the appearance and provide corrosion resistance. The aluminum is then carefully inspected for quality before being packaged into coils or sheets for delivery to customers, ensuring it meets the required specifications for various industries.